Here is practice problem 3, part of organic chemistry, naming of compounds. So it says the letters A to F in the table below represent 6 organic compounds. Let's start off by analyzing what we have. So compound A, we notice that contains only carbon and hydrogen. It is a hydrocarbon, so we are expecting it to either be an alkane, alkene, or alkyne. But if we look closer at this, and you can actually draw it out to see what it is, this is going to be an alkane. Compound B is butanol, that is part of aldehydes. Compound C, so we notice this contains the OH, that is the hydrazole, so that is definitely an alcohol. Compound D, notice the halogens Br and Br, that is a haloalkane. Compound E has a double bond oxygen on the second carbon from the right, so that has to be a ketone. And compound F, we have CXHYOZ. So because we don't have values as the subscripts, at the moment, we are not sure what compound that is. We're not sure what homologous series it belongs to. But we know that it could be anything between ketones, aldehydes, alcohols, carboxylic acids, and esters, because those are the compounds that contain oxygen in them. 2.1 says, is compound A saturated or unsaturated hydrocarbon? Give a reason for your answer. Now, when you look at compound A, it is an alkane. We know that alkanes are saturated hydrocarbons. So this is going to be saturated, and the reason is because it contains only single bonds between the carbon atoms. There we have it. Now 2.2 says write down the letters that represent each of the following. So 2.2.1, we are looking for a ketone. Ketone, we can see here, is represented by E. The next one we're looking for is a haloalkane, and that was compound D because it had the bromines on it. 2.2.3, two functional isomers. Now remember, functional isomers that you've learnt about are only two. They are carboxylic acids and esters, or ketones and aldehydes. So we did come across a ketone and an aldehyde here. There's our aldehyde, compound B. It's butanol. It contains 4 carbons. And also the ketone contains 4 carbons. So they are functional isomers of each other. The answer is B and E. Okay, we're on to 2.3. It says consider compound C. Is compound C a primary, secondary, or tertiary alcohol? Give a reason for your answer. So let's have a look at compound C. So here's how we identify this. We look at the carbon that contains the hydrazole group. And on each of its 4 bonds, we see how many carbons it is bonded to. So notice that this carbon that contains the hydrazole group is directly bonded to one other carbon, meaning that this alcohol is a primary alcohol. So it's primary alcohol, and our reason is the carbon containing the hydrazole group is directly bonded to one other carbon atom only. Now 2.3.2 says write down the structural formula and IUPAC name of a chain isomer of compound C. So let's have a look at compound C. It's the same alcohol that we're working with. And what is a chain isomer? So those are organic compounds that have the same molecular formula but different chain length. So what we need out of chain isomers is that their parent chain length has to be different. Here the parent chain has 3 carbons. What we can do to create a chain isomer of this compound is we can take this methyl branch and add it onto the parent chain. So we would now have an alcohol with 4 carbons in the parent chain instead of 3 like what we have in C. So to do this, Let's start off by writing down 4 carbons. Keep the OH where it was, okay? So this is not a positional isomer. In a positional isomer, you would move the position of the OH. This is a chain isomer. So all that needs to be different here is the chain length. What we did is we took the methyl, we added it onto the parent chain, and now we made it an alcohol with 4 carbons in its parent chain. So we have increased the chain length. Now, they wanted the structural formula as well as the IUPAC name. So we don't have any branches here, but the parent chain has 4 carbons, so it's going to be butane. The OH is on the first carbon, so that's going to be 1-all. IUPAC name here is butane-1-all. For 2.4, it says write down the 2.4.1 IUPAC name for compound D. So let's have a look at compound D. This was our haloalkane. Let's just erase what we have. Remember, your first step is to find the longest parent chain. So let's see how many we get. We can get 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. 7 is the longest parent chain. So we take the parent chain this way. Then it's quite obvious here that you need to number left to right so that your bromines lie on the lowest carbon atom. So let's number. Now, by numbering in this way, we notice that the bromines lie on the second and the third carbon. Because we have 2 bromines, we know that's going to be dibromo, and we need to indicate the position of both of them. Then we also notice that on the 5th carbon, we've got a methyl branch. Remember, branches are always named alphabetically. So even though it's dibromo, we still look at it as starting with the B because it is bromo. So to write out this IUPAC name, we have, so it's going to be 2,3 dash dibromo dash. Then remember, on the 5th carbon, you had methyl, so 5 dash methyl, and the parent chain contained 7 carbons, so that's going to be heptane. Here's the IUPAC name. 2.4.2, they say name of the functional group of compound B. So let's have a look at B. B is butanol, part of aldehydes. Aldehydes contain a carbonyl group. So that is carbonyl group. And you may notice this in some memos that instead of carbonyl group, they use the term formal group. So according to your syllabus, the more correct term would be carbonyl group, but if you do use a formal group as well, you would get your mark. And 2.5 says a sample of compound F contains 40% carbon, 53.3% oxygen, and X% hydrogen. Now just to remind you, compound F was given without the subscript, so we had variables CX, HY, OZ. So we kind of see where this is going towards, right? We're given the percentage composition here. 2.5.1 says, if the molar mass is 60 grams per mole, calculate the molecular formula of compound F. So this is something that comes from grade 10. You learned how to do empirical formula and molecular formula, part of your stoichiometry, also known as quantitative aspects, in grade 10. So when you were first introduced to the section. So here they are testing you on your grade 10 knowledge. Now here's the thing. If we look at the percentages that are given, you know that you take them as your masses. So you use them directly as your masses and you can calculate number of moles. However, what we notice is that we don't know the percentage of hydrogen. But since this compound is made up of carbon, oxygen, and hydrogen, it means that together, all 3 elements make up 100% of the compound. So since we know the percentage composition of the other 2, to get the percentage of hydrogen in this compound, we just need to subtract the other two from 100. So if we take 100, that's 100%, and we subtract 40% minus 53.3%, we see that X here would be 6.7%. So they left that as something for you to think about, because remember, you in grade 12, they're testing you on grade 10 knowledge. They're not going to test it to you in an easy way. So they're going to test it to you in a way that actually makes you think about this. Now that we know what X is, we've got the percentage composition of each element. So we're going to use that as is as their masses. So here's the order that we're going to work with. We're going to work with C, then H, then O, since that's how it's given to us in that formula. We're going to have mass of carbon as 40 grams, mass of hydrogen as 6.7, the one that we just calculated. Mass of oxygen was 53.3 grams. Our next step is to calculate number of moles. So we're going to have mass over molar mass. So carbon is going to be 40 divided by 12. Remember, molar mass you get from the periodic table. Okay, so this gives us 3 point, and there's many threes after the decimal. Moles. Then let's calculate number of moles for hydrogen. Again, mass over molar mass. Now you know that the molar mass of hydrogen is 1. So 6.7 divided by 1 is still 6.7. And let's calculate number of moles for oxygen. Molar mass for oxygen is 16. That gives you 3,33125 moles. Once we have the number of moles, we're now going to create a molar ratio with all of these. Now, the whole purpose of your molar ratio is so that you can simplify these to whole numbers. To do that, we are going to divide throughout by the smallest number, and the smallest number here is 3.33125. There we go. Now let's simplify. So the first part gives us 1. In the middle, we have 2, and on the right, we have 1. Now, this gives you the empirical formula, which is going to be CH2O. But they asked you to get the molecular formula. So it's always your first step, right? When you ask to get molecular formula, you have to get empirical formula first. Now that we have the empirical formula, we are going to calculate the molar mass of this empirical formula. So we are getting the molar mass of CH2O, which is going to be 12, plus 2 times hydrogen, which is 2 times 1, plus 16. That gives you 30 grams per mole. Your next step is to create a molar ratio between your calculated molar mass and the given molar mass. Remember, in the question, we were given the molar mass as 60. So we're going to have 30 is to 60. We're now going to divide throughout by the smaller value, which is 30. This now simplifies to 1:2. And you now take that bigger value and you multiply your empirical formula by it. So our empirical formula was CH2O. If we multiply that by 2, we get C2H4O2. So that is your molecular formula. (2.5.2) says, write down the IUPAC names of 2 organic compounds that will have this molecular formula. So 2 organic compounds that are going to have this molecular formula. To understand exactly which 2 compounds have this molecular formula, if we pay careful attention to the formula that we ended up with, we notice that we have O2. this particular compound has 2 oxygens in it and 2 carbons in it. So we can think of a carboxylic acid because carboxylic acids have 2 oxygens. And a carboxylic acid with 2 carbons would be called ethanoic acid. But they wanted 2 carbons, okay? So ethanoic acid would be 1. What about an ester? Esters also have 2 oxygens in it. But for this to be an ester, if there are only 2 carbons, 1 carbon has to be the branch, then the other carbon has to be the parent. So the name of that ester would be methyl methanoate. So these are 2 different compounds that will have the same molecular formula as C2H4O2. Please remember to like, subscribe, and turn on your notifications for more content.